Now we have used the amplitudes, and as I say, I don't have to write now expression up for a CCSDT energy, because that's this. It's just a question how you got your amplitudes. So the difference in the couple cluster methods is not in the energy expression, but it is in the expression for the amplitudes. So how to get the amplitudes? How to get the amplitudes? We're going to do the same as on Tuesday. We're going to do this precisely the same as in Müller-Blaser perturbation theory. We have our equation, and we like it best in this form. But one can also do it. Oh, sorry. Now there's an e to the t for too much. We like it best in this form. One could also do it without that, and having the e to the t, it gets slightly more complicated mathematically afterwards, but you get to the same equations anyway. This is just sort of a bit faster. Now, how did we get the coefficients on Tuesday in Müller-Blaser perturbation theory? We projected against other Slater determinants. So we're going to do precisely the same. In order to get the energy, you project against the reference Slater determinant with Hartree-Fock. In order to get the equations for the coefficients, which we call amplitudes here, we project against other Slater determinants. And we're going to do that sort of for each type of coefficients, single, double, triple, quadruple coefficients, we do that sort of separately. And you do it, I mean, we saw that when we did that on Tuesday, when we project against one particular Slater determinant, we got actually the coefficient for this Slater determinant. And that's going to happen precisely the same here now. So we project against excited determinants, and let's call them M, E, dot, dot. Remember I, J, K, L, M, N, those are the occupieds. A, B, C, D, E, F, maybe also G are the, G are the virtuals. So this is an excited determinant. If I do that with this expression, then I get for the general case where I haven't specified how far I go, that's the dots, could be single, double, triples, and so forth. E to the minus t, Hartree-Fock, Hamiltonian e to the t, phi Hartree-Fock. And then I get E couple cluster, and now I get my phi M E dot 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 phi Hartree-Fock. And what does that give me? Now I have some kind of excited determinant and the overlap with the Hartree-Fock determinant. And since they are all orthogonal, this is 0. So the right-hand side becomes 0. And it does that because we did that trick. We pre-multiplied with the e minus t, which removed the e to the t here, which made sure that I just have Hartree-Fock standing on the right, and therefore this gives me 0 immediately. So I end up with the expression where I have a 0 on the right-hand side, and the energy is out of that equation. As I said, if you don't do it, you still can get to this equation, but it takes half a page longer. There's no reason to do that. So let's take a singles. For singles, then I have phi and E. That's a single excitation. Now I have to expand the e to the minus t. Remember there's 1 minus, because it's minus t. And now the question is, how many excitations do I have to include? Before, when we calculated the energy and we came from the left with how to Fock, all the excitation operators disappeared because they tried to de-excite that determinant. And because it was hard to Fock, there's nothing to de-excite. And that's really the place where this excitation becomes so weird. It would be so much easier if it would be replaced the occupied orbitals replacing operators. And if there are no, and then if it acts to the left, it becomes a virtual orbital replacing operator. And if there are no virtual orbitals, there's nothing to virtually orbital replacing. And then it gives 0. But now we have one virtual orbital in there. So now, but only one. So now we can have T1 standing here. And if it would be double excitation, we would have 1 minus T1 minus T2. If it were a triple excitation, it would go to T3 and so forth. But all those squared and cubed terms, well, you have to take as many as it fits to the excitation level of this determinant here. Then I have my Hamiltonian here. And then on the right-hand side, I have to go, I guess, up to here, T1. Then I have T2. Well, let's stick to the normal mathematical parenthesis notation. T1 squared plus T3 plus T2, T1 plus 1/6 T1 to the third. That parenthesis phi hard to Fock is equal to 0. Why do we include? And I haven't written any dots here. So that must be all contributions which actually can give something. Why is that? Well, what do I have on the left? I have either a single excitation or the single excited determinant de-excited hard to Fock. I mean, this is going to give me hard to Fock back. So I have hard to Fock or single. And I have still my Hamiltonian as always. So it can be 2 up or 2 down. So if that's hard to Fock, then I only can have double excitation on the right-hand side of the Hamiltonian, because otherwise the Slater-Connon rules say no. So I can have this one and that one. But if that's a single excited determinant, single from Hamiltonian, and can go up to the triples. Therefore, I have to include all operators which sort of give me triple excitations. And then you can imagine if I come here to double excitation, I have 1 minus T1 minus T2. I have all that plus the quadruple excitations. So I get here now for each single excited determinant, I get one equation, which is going to involve, of course, the amplitude of this. But unfortunately, it's going to include all the other single excitation amplitudes, all the double excitation amplitudes, and also triple excitation amplitudes. Then I can do the same for, as I said, for double excitation, M, N, E, and F. And I get an equation which is, I mean, it sort of starts with 1 minus T1 minus T2, Hamiltonian, and then the parenthesis starts as it does here. But I get also with T4 and all quadruple excitation. All those equations, they are all coupled. This is a huge set of nonlinear coupled equations, what comes out of that. But up here, I have this thing here, which, I take the original Schrödinger equation and I project the Schrödinger equation against a particular determinant. Because this is this is just a determinant, there's no coefficient in there, this is just a determinant. But that determinant is orthogonal to the Hartree-Fock state. So the right-hand side of the expression always becomes 0. Never mind what happens in here, the right-hand side is always 0. And that means this matrix element is going to be 0. But you're absolutely right, I have the, whenever a t stands here, that means I have all those coefficients in there. And that means all those set of equations, so the equations for the single amplitudes are coupled to the equation for the double amplitudes, are coupled to the equation for the triple amplitudes, are coupled to all of them. So I have a huge set of coupled equations, and because I have things like this in here, T1 squared, which means I have this kind of product of single amplitudes, these are nonlinear equations. Which makes it slightly difficult to solve them iteratively in a way like Hartree-Fock. Because this equation here, that is one equation. Because I come with one determinant, and I can write that equation in a way that I have the coefficient, the amplitude for this determinant standing on the left. I think Frank has the expression in the book, but it's too long to write. And then I have something standing on the right-hand side. And that is an integral plus a lot of terms which has all the other amplitudes, the singular doubles and the triples amplitudes included. So you get equations which sort of depend on its own solution again, like the Hartree-Fock equation. You have to solve them iteratively. You have to choose something which you put in on the right-hand side, and typically what you do is just set them all 0. And then you can solve them, and then you insert it again. And the interesting thing is, if you do that with the double equation, that's the equation for an amplitude of a double excitation, and have some integrals around the right-hand side, and all the other amplitudes. If you set all the other amplitudes to 0, what you get out for that 0th order or first iteration of the CCSD doubles equations is actually the MP2 doubles amplitudes. So MP2 is actually just the result of the first iteration of CCSD.